Greetings. I was doing a comparison between ReLU and LeakyReLU and came across an interesting situation. So let's look at how these train. I call this a roller coaster shape because you've got weights and set up in the first epoch or two, and then this long flat, it's kind of like the top of a roller coaster, then whoosh. Notice what's bouncing on the bottom here. In comparison, standard ReLU has got this nice smooth curve. I think of this as taking a step halfway towards the wall infinitely. It got a little better average error per epoch. If we did follow this out to about 500 epochs, ReLU would be better. Leaky ReLU gets you there quick. If you had to have the best prediction, you could run more compute to figure it out with ReLU. But can we get the best of both worlds? So if we look at the difference in models here, notice AutoML selected Xavier for ReLU. I always use a learning rate sweep. The learning rate for ReLU was 0.001 compared to 0.01 for Leaky ReLU. So there was really three differences between these models. And learning rate was my first suspect, but that didn't do it. Let's try changing the alpha on the Leaky ReLU from 0.01 to 0.001 and see if that helps us avoid this bounce. Let's take a fast look at exactly what we're changing. Here's where we've got our ReLU functions defined in our activation functions file. So ReLU, very simple. Give me a number. If it's positive, I'll give you the same number back. If it's negative, I'll give you a zero. Leaky ReLU, in contrast, says, give me a number. If it's positive, I'll give you the same number back. If it's negative, I'm going to let 1% leak through. I'll give you 1% of that number back. And the thought behind this is that it will prevent dead neurons or revive them back to life. And this 0.01 is where that 1% is defined. So we're going to create tiny ReLU and make that 0.001. In other words, same thing as leaky ReLU, but a tenth of a percent instead. So let's see what happens. We have tiny ReLU as the activation function of our 4 hidden neurons. Let's start running it. You can see it's turning through the epochs here, but there's a couple of hints. Number one, our bias and weights aren't even showing up here. Number two, look at this error history graph. We've got a gradient explosion at the end of this thing. And we're almost to it. We're at 80 of 91, and here it comes. Bam. Look at that. What's out is that we had a beautifully behaved, nice model. And then at 91, it explodes. Granted, we all probably get more gradient explosions than we'd like, but don't they normally happen around epoch 1? How often does it behave nice and then blow up out of nowhere? So I wanted to understand what was going on with that. Let's take a look. We can back up a few samples here. So it exploded on sample 25, officially exploded to the point where we said this thing is over. Starting here at 21, we've got a negative activation. And what that means is when the back prop comes, it's going to have an activation gradient of 0.001. So the output neuron gave back an error signal, you can see in the bottom right corner here, of negative 155. But we said we'll take 1/1000th of that, essentially like a dead neuron. But for the first time in the run of this model, this thing flips positive. And look what happens to that activation gradient. It goes from 0.001 to 1. It increases by 1,000. And now when the error signal, except blame, comes back, negative 1,291, it says, I'll take all of it. And all of a sudden, it went from sample 21 accepting negative 0.1 to accepting negative 1,000 blame. And on the sample after that, 138. And on the sample after that, I don't even know that number, 1 followed by 13 zeros. And then it's out of there, blown up. What makes that weird, nice, well-behaved model, and then all of a sudden, poof. So I thought that was pretty interesting. I hope you did too, and thanks for tuning in.